Now I see actually your microphones as well with a red cross. That probably means that muted. And I'm assuming that you're hearing me. Thank you. Let's wait for a minute for the others to join. In the meantime, if there is anybody with a question, you can type it in or turn your microphone on. All right. The question that is raised is the sign of the derivatives. And Alex says the values in the vector are not always all positive or negative. And that is possible. That is, some of the derivatives may come out to be positive, some of them may come out to be negative. It all boils down to how the value of psi wu factor is changing as a function of a particular orientation angle. So it is possible that some stresses, some stress components will increase, some will decrease as a function of a particular value of a design variable. So there are basically 3 stress components in each layer. And when we compute derivatives, we're computing derivatives of each of these 3 stress components. That's sigma 1, sigma 2, tau 1, 2, with respect to a variable. And in your case, thickness of zeros and thickness of 60s and minus 60s are the thickness variables. And as I said, if you increase the thickness value in one particular orientation, it may cause some of the stresses to go up, some of the stresses, components to go down. If you increase the thickness of the plus 60, some of the stresses in some layers may go up, some may go down. So that's completely okay. The confusion comes from the fact that when we call the Psi-Hill subroutine, it actually pays attention to the sign of those quantities. But that's built into the equation. And there is nothing that changes in that equation. So if the stresses are all positive when you do the base analysis, that does not mean that the derivatives are going to be all positive. Derivatives are simply an indication of completely something different. It's how the magnitude of a particular component changes, either in the positive direction or negative. So it's just a sign. Sign means there, whether if it's positive, then that particular stress component is going up as we change the thickness, and the ones that have a negative sign, those stresses are actually reducing. So taking those signs, leaving without touching them, should work, provided that the linear approximation is done properly. There is still the issue of whether this methodology is going to work. That is, in the case of max stress or max strain, if you remember the plot of the stresses, those maxes are just straight lines. For the shear, for the normal stress, they're straight lines. And when we make approximations to those as straight lines, they may not be horizontal or vertical, they may come some angle, but nevertheless, being an approximation, nevertheless, they very nicely bound the design space. In case of Saiwu, which I'm actually recommended that everybody change to Saiwu criteria, that envelope, which is actually 3D and ellipsoid, is being approximated by a plane, linear in variables and most likely linear. So when we do that, whether they are going to actually send the optimal solution in the right direction or not is highly questionable, unless you start putting move limits. So move limits is, in my mind, an essential component of this activity, that it's becoming apparent that without move limits, this methodology may not work. The second reason why this methodology may not work, even though the move limits prevent you from completely going haywire, they may still send you a part of the design space that is infeasible. And making another approximation from that point should theoretically bring you back to the inside the feasible design space. Unless somehow there's a conflict in the constraints that would not actually allow you to accomplish that. So this is the purpose of this exercise, to find out if linearization, which is a very typical engineering practice, whenever we have difficulty in solving problems that have some nonlinearity, we always, as engineers, go to a linear version of things that is easily solvable. And we know that the linear programming does work for max stress and max strain. So ideally, there shouldn't be any reason for this not to work. But this is your project, so this is something that I'm hoping that by looking at this problem, you'll have at the end a better understanding of the behavior of stress constraints and how stress constraints act in the design space. Those of you who have asked questions regarding this during the office hours, I did work with them and showed them a few things. Those who did not, I'm going to show one thing that I added to the program that may be of some value for you, that I think you may want to play with and see if you can actually get get some understanding of the behavior of the stress constraints, is I added the feature to plot SIVU constraint, SIVU stress constraint. So I put that into the program file, and program file is actually loaded to Blackboard. It's the latest version of CLT program called 4.3. So in the previous version, I had some evidence of it, but it clearly said that this is not working, work in progress. Now those things work. And what I'm going to do, basically flash that on my screen, which will require me to actually share my screen. Share application screen, allow. All right. Let's go to the solutions, solution 2, solution 2. Okay, this was the template that I was preparing. So let me make sure that I start from clean slate, quit kernel. And open also my program and load it. 4.3. Which is here. And just to show you what is added there, let's copy, find SIVU. I'm going to try to find the places where SIVU is mentioned. SIVU failure is already there, that is working. Plot SIVU envelope is the new program. Plot SIHIL envelope is still not working. If you go to SIVU, it explains what SIVU program does, and that's what it does. If you go to SIVU envelope, although it says under development, actually most of it is working. Only a portion of it is not working, which is not necessary at this point. And let me explain what that is. It says the module is to 3D visualization of SIVU envelope, failure envelope, given a symbolic list of sigma 1, sigma 2, and sigma tau 1, 2. So in the input, you're going to be providing this as symbolic values, just like it shows there. And and then you give the numeric values of the limits of the stresses, principal material direction stresses, strength. And if one of those stresses in the list here is a number, 1 of the 3, then instead of making a 3D plot, it makes the 2D envelope, which is a splice of the 3D envelope at that particular value of the numerical stress component. If all are real values, sigma 1, tau, sigma 2, and tau 1, 2, this is the part that is not working. It should also put the point in the diagram showing you where your stress state is with respect to the given failure envelope. This is the part that is not working because it's just a programming thing that somebody has to sit down and do the appropriate branches. So with that, if I go in here and execute those, I didn't execute my program, run all code, that is executed. Now I can run this again. Everything is in there. And I'm going to actually run much of these very quickly without stopping anywhere. And I'll show you how this graphics feature is working. This is still part of the template. If you don't have this template, I can send it to you. There's the midplane strains and one given value and the stresses and the transformation matrix and stresses in principal materials, defines the load cases. This is the failure envelope. So if I call the SciVu envelope with sigma 1, sigma 2, and 0, let me do the all symbolic version first. Copy this. And tau 1, 2. It creates the failure envelope. This is actually an odd-shaped failure envelope. The axes are sigma 1, sigma 2, and tau 1, 2. So any point inside this ellipsoid shape is feasible, doesn't violate constraints. And if you want, you can change I will change the options so that you can actually see the inside. This will be some of the transparent ellipsoid. But this is basically the envelope, failure envelope in the sigma 1, sigma 2, tau 1, 2 coordinates. Not many people show these in books as 3D. Most people show it for 2D envelopes. And that's what these things are going to do. So if I actually say, make a cut along the tau 1, 2 direction, and if you want that cut to be at 0, 0, this is going to be what you're seeing. So this is probably a cut in this plane here, showing. And if I actually change this value to, the values were up to the 10 to the 8, so I'll make a 1.0 times 10 to the 7. Hopefully I will make a cut somewhere inside. No, it didn't take this value. So it's just doing the 0, 0 value right now. Let's assume it that way. That it's making the cut at tau 1, 2, 0, 0. If you cut this spherical shape along in the sigma 2 plane, so coordinate axes are now sigma 1 and tau 1, 2 in the vertical. This is the cross-section of the ellipsoid, and if you make the cut for tau 1, 2 equals 0, then you get this shape here. Don't know why 10 to the 7. Let's do 0.8. 8 times 10 to the 9. Okay, it disappeared, meaning that I'm on the outside 6, outside 5, I'm still outside. If I make this 8, there. It's back. Let's make it 8. Okay, so this is actually a smaller envelope. So the cut that I'm making is somewhere inside this, and this is the domain of feasible sigma 1, sigma 2. So I'm making the cut along the tau axis and seeing a cross-section of this ellipsoid. So this is why this might be useful, because when you make the linearization with respect to M's and N's, you may still be able to plot these things and see where your approximation is. If you make the approximation with respect to stress components. However, in this particular case, we are making the linearization with respect to thickness variables. So I need to be able to convert everything to thickness before we can actually see the linearization. But in any case, this is a pretty important part of any design process, that you have some sort of a failure criterion. And when you implement that, that is what limits your stresses in the individual plies. Okay? And those will enable you to change your thicknesses and orientation angles to bring you inside this failure envelope, whether it's psi Hill or psi Wu or some other criterion. In fact, there are more than half a dozen of these, about a dozen maybe, that are respectable ones. And they change in shape somewhat. Obviously, max stress, max strain, they become straight-based objects in 3D, and they are not parallelograms. They're actually quite arbitrary shapes, but each face in the X, Y, and Z, or tau 1, 2, and sigma 1, and sigma 2 will be straight planes, creating this envelope for the failure. Okay, any questions about this? This is now this plus psi Wu envelope is available for you. The only thing that is not working is if I actually take these and make all three numbers. That means I want to see my point, whether it's inside this or outside this. That is not working because I need to call the subroutine itself once I call it with all numbers. So that particular one is not going to be working. So you can see that by, let's say, putting these values. Let's say I put this. Let's make it 1.8, and it will come and tell you this is not working yet. But if it worked, it was going to put the given point, which is the stress point, on this diagram. And you will see whether it's inside or outside. If it's outside, it's failing. If it's inside, it is not failing. So I have a psi Wu number which is less than or equal to 1, less than 1. Okay? Any questions about this? Unless somebody is typing, I consider this to be another question. All right. So I am assuming that most of you are getting pretty close to solving this problem. If you cannot, if it's not working, you will need to start understanding what's working, what's not working. So put some text into your file explaining what you're doing. I will not accept any submission without some text that explains what you're doing. Okay? And let's put a deadline on this so that we can't go forever with this. I really want you to put some effort into this and get as close to the solution as possible and I'm willing to help you with that. I have some email problem that I cannot get my email on my computer, but maybe what I will do is I will open another account somewhere, and you can send your files there so that we can one-on-one. Wait, was there another project assigned? Okay. Addison, this is the same project. This is the second test project. You may have submitted yours, but there are still a bunch of people who have not submitted theirs. And okay, my apologies. All right, no issues. If you want to double check your submission, you can do that. But I think we need to put a firm deadline now. And if you don't raise your questions about this and get help during the office hour, then or send me a file that I can take a look, then we're going to go with that deadline. And the deadline will be next Monday midnight. We got only 4 lectures left, including today. And next Monday midnight is the last deadline for the second project, so that I can give you one more project for the final. How was that? Do you like that? Very quiet. Okay, let me. Yes, please. Thank you, Mary. Let me tell you what I hope the final last project is going to be, which basically completes everything that I wanted to do this semester. And that will be the genetic algorithm design of a composite laminate. Okay, this is the only algorithm fully capable of handling every kind of nonlinearity without linearizing or anything. If you have a working failure criteria, working stiffness criteria, this approach should take that and be able to do it. Of course, this is a design activity, which means it's not just one single answer. Most likely, everybody's going to come up with different answers, but that actually is what it is. So that really completes what I consider essential. Now, if I had more time this semester, which I didn't because we spent actually quite a bit of time in CLT. I'm hoping that in the future I won't spend as much time with CLT. I will bring everything to a point that even if you don't have CLT background, I'll basically have you do your own reading and running tutorials yourself, so that I don't have to lose any time on the CLT portion, the analysis portion. The only thing that we haven't done, or 2 things that we haven't done, which are kind of, it's nothing entirely new, but it is important for composite design optimization. Number 1, different analysis approaches, theories. So you need to be exposed to at least one additional theory that takes into account interlaminar stresses between the layers. Nothing we have done so far is capable of taking into account those stresses. So you need to at least go to first order shear deformable theory to be able to get the basic information about interlaminar stresses between the layers that try to actually separate the layers that cause delaminations. But it's just another analysis that gives you stresses. So just like having sigma 1, sigma 2, tau 1, 2 in a given layer, you will also have stresses between layers that will have some measure of separating between them, and that will become a constraint in the process. Let me read the question that is raised. If you have already submitted project 2, is there anything additional that we must submit? I noticed you were creating some plots. Should we attend these and submit them in addition to the project? If you're confident with your answer, David, you don't have to. If you think that you may have missed something or you're not getting the right answer and there's something maybe is not working, and you try to understand that by looking at where you're ending up with your solution in the Saibu diagrams, that your design is actually satisfying the constraints, which if your constraints are coming from the fine minimum, they're satisfied. But if your constraints are not right in calling this fine minimum, and you do the analysis of your final design, and you find the design point outside your lamination envelope there, not lamination envelope, the strength envelope, then something is wrong. So the only benefit of these failure envelope is to be able to tell if you're satisfying all the constraints. Then you don't need graphics for that. You can actually recompute the Saibu number at the final design. If it's less than or equal to 1, it means it actually satisfies. So that is my answer. Is that all right? Okay, very good. So coming back to things that we haven't done and we won't have the time to do, interlaminar stresses and constraints associated with design is actually important when it comes to shear failure. We haven't looked at shear failure between layers and designing for shear failure between layers. But as I said, all the methodologies that we do and the failure constraints we implement are applicable to those as well. So it's just a matter of doing different analysis. Of course, if you are going to be doing sequential linearization, then based on the new theory, there will be a new equation for derivatives. That is something that that's going to make it more complicated. So that's one of the things that we have not done. The second thing that we have not done, connecting this kind of capability to more off-the-shelf analyses routines. Right now, we're doing very simple analysis, and we're getting some stresses, sigma 1, sigma 2, tau 1, 2, and we're happy based on this information. Our geometry is nothing like a complex geometry. In a complex geometry, you have stresses changing from one point to another, which means that you need to start following these constraints and design methodologies at different design points. These are called point designs. So there may be multiple point designs evolving at the same time. And depending on how your design changes from one part of the structure to another, you may want to start dividing your domain into multiple segments and use different layups in different segments, or design one layer that satisfies all the single point constraints. And in that case, you're going to have a heavy design if you use one layup for the entire domain. But that becomes a very complicated process. That actually, unless you're a graduate student really working on this particular topic of designing a composite part, we don't normally get into those. When you get into those, you may require different layups in different parts of the structure. This is called, dividing your structure into subsections and designing those subsections separately. And then you try to actually blend those designs to one another, because nobody designs one layup here, another layup here, and puts side by side. You always have some transition of layer from one part to the other, which is quite a complicated thing. but it really is, when you have that capability, you're already an industry level expert working on it. It's not just the basic design course, but really you're an industry expert working on this. So finite element connection with multi-segmented structures and then blending them to one another. So that's the other topic that we haven't done. And are they not important? No, they're important. But they are built based on top of what we have covered so far. With the inclusion of completely nonlinear design, there won't be any, of course there is always refinement of tools. More efficient design tools will require some additional information from us in terms of behavior. But for the basic course in design, what we have covered should be completely sufficient. So that's why I'm trying to desperately finish the GA so that you'll say that if you have a GA, somebody gives you a GA, you'll be able to design with it composite structures. But if they also say use finite elements to do this, then you will need additional talents, capabilities, and tools to actually do this. At that point, either your institution is going to give you additional or standard tools that they use internal to a company, which can vary quite a bit from one company to another. And some companies may not even have those capabilities. They may still designing based on rule of thumbs and what appears to be a good design. Don't underestimate that. A lot of people still do that these days, even including major companies. They don't necessarily have all the fancy tools. This is still an area that actually is begging for good solutions in the industry that engineers can jump into very easily, but they don't really exist, to my knowledge. So it's a very limited area, of course, but there are major companies that really want these kinds of capabilities and talents that are capable of using these kinds of tools. Okay, so that's the summary of where we are and where we are going to accomplish before the end of the semester. And provided that we complete the tutorial in 1 week, we'll have 2 lectures left to perhaps start the final project that we're going to try to design a laminate using genetic algorithms. Any questions? All right, so let me save this. So we completed the lecture on this, and I believe, we're just starting okay. The answer is from Sam is for project 3 we'll only have 2 classes to work on it. No, there's more time to work on it. So the final exam week or end of the final exams, 1 day before the final exams is probably going to be the submission date for this, and last day of exams, I don't have my calendar on this computer anymore. I have to look at final exams, 5th, May 5th. So you'll probably have until Monday the 3rd, end of the day, Monday the 3rd, for that, which will give you, I guess, a little over 2 weeks of time, almost 3 weeks of time. Is that reasonable? Now, the last week, 2 classes, we're going to actually start defining our problem, and I'm going to help you to actually have some starting template that we can go with it. That doesn't exist. Although we have worked on this kind of programming for companies and made them tools to use, I've never actually assigned this problem to a class before. I may have some simple version that I assigned, but so this will require some work from my side as well. So I'm going to spend the last week working with you guys on that. And of course, you're only responsible from whatever I'm able to teach you. Now, of course, I make some assumptions regarding what as to what I was able to teach you, and you have some understanding of what you have been able to learn. And I'm a pretty standard, old-fashioned faculty, so I still have the notion that I still teach you. I don't, what is the term? I'm not doing learning activities. I'm trying to teach. If I were to be a younger person, I would probably say that we'll have some more learning activity on the last week so that you can learn more, which is, of course, the case. That's your job. And my job is to do my best to teach it as best as I can. And if I can't, that's my failure. If you don't learn, that's your failure. But of course, these two will never overlap. There will always be a gap in between. That's the gray area. That's the gray area that either means that I don't know what the heck I'm doing, or you don't know what the heck you're doing. I'm harsh sometimes, I'm sorry. But I take responsibility for it. All right. Gentlemen, and nobody understands my jokes. I had a eye exam appointment today, and the gentleman asked how was my spiritual life, and I made a joke about my spiritual life. And at the end, he was looking at me. He didn't understand anything. So my jokes are strange too. Would you like to hear that joke? Good. It's good for you not to hear it. All right, let's go to the lecture. Abi the tutorial. The joke is about meaning of life. General. And I'll do it once we are done with when we have some free time. All right, so this file, let me clean the slate again. Evaluation, quit kernel, quit local kernel, quit, and cell delete all output so that we would know what we are doing. And it will require a program that has my genetic algorithm modules. And let me open that file from the programs. And that is the unified version. And it looks something like this. So if I run all the code and come back and type here question mark star GA star, there are a couple of Mathematica internal system operators, JRCH process and net GAN operator. Those are not mine. The ones that are in genetic algorithm are mine, and they have GA, and they have decode GA, they have mutate GA, and run GA. So let's start with the question mark GA and see if this tells something. I tried to make it the way the other program is. So it says following modules. For initialization, there's a module called init for population initiation, which is not listed in here for some reason. Decode binary, decode GA, mutate GA, select one, and run GA. So some of these things are apparently outdated. I made running the GA run GA rather than just GA, and not sure if I define these things yet or not, but as we go along, we're going to find out. So this is initialized. I'm going to skip this initialization thing. And very quickly, this is something that we have done. A typical typical optimization algorithm searches the design space jumping from one point to another. So this is, for example, like a steepest descent algorithm. So minimum is here or a maximum is here, and it's trying to find the minimum or maximum by jumping from this design to another one, following an algorithm. So at every step, it's jumping to a new point and approaching towards the optimum, but sometimes very, very slowly. So it can take hundreds of iterations. Whereas GA, as we mentioned, is a process that jumps from one population to another. So let's assume that we have a population of 10 designs, and in the initial population, they are distributed in the design space in this fashion. Out of these designs, we evaluate their fitness, we do crossover mutation operations, and you get a second population, which is a little different than the first one, and hopefully approaching this somehow. It's not there yet, but if you go to the third population, there's already a design here, and all of these are actually now approaching here. And the next one is more of them approaching, and at some point they're all approaching to a single point. This may have actually used no mutation in the process, because if there was a mutation in the process, occasionally, or maybe more than occasionally, some of these designs that are approaching here will be mutated and they will just go out someplace else. And if this is a multi-objective function, then you will not be converging to a single point here. So you'll be able to find designs that are elsewhere through the mutation operation. And this is a typical case for composite design, that different layers acting differently may be controlling the design from different perspectives, from the strength and stiffness and the vibration frequency perspectives. So there may be actually multiple things happening at the same time. And if you formulate as one objective, sometimes this going out from a specific point, converging to a suboptimal design, will be prevented with the mutation. So that's what this is. Now, how do we make the coding of the design variables? Because in engineering problems, we have either thicknesses as continuous variables, or ply orientation angles as continuous variables, or thicknesses that are discrete numbers, or orientation angles that are discrete numbers. So in case of discrete numbers, imagine that if I limit myself only to integers, most of these points are not going to be valid. Only points at 1, 0, -1, and -1 here, 0, 1 will be feasible. So that's a discrete problem. And GAs cannot handle that. But my traditional optimization algorithms doing the search based on this kind of a scheme cannot, because derivative information would become meaningless and so on and so forth. So we code the design variables, which are engineering quantities, either continuous or discrete, into either a binary string with 0 ones or another alphabet like 1, 2, 3 for 0 degree flights, 45 degree flights, and 9 degree flights. Let's assume that we are doing binary coding. So I take design variable 1, and let's assume that it has a value of 35. That 35 is a number assigned to this design variable x1. If I convert it to a binary number, converting a number to a base form is base form number, and you give how many alphabet you have. 2 means binary. So binary representation of 35 is 1, 0, 0, 0, 1, 1. If this was another alphabet, ternary alphabet, so it will use zeros and ones and twos, then the same number 35 will be represented by 1, 0, 2, 2. So there's hexadecimals and other alphabets that people use for representing numbers. But of course, if I use base number 10, not 19, I'm sorry, I get 35. A representation of 35 on base 35 is 35. But we want binary representation, which is a little string of zeros and ones. And in this case, it's 1, 0, 0, 1, 1. It turns out that I can actually take these by using Mathematica's built-in integer digits command. So bx1, binary design variable x1, is base 2, and their integer digits. So I get a list of 1, 0, 0, 0, 1, 1. This is exactly what I want. This is one design variable representing the string of zeros and ones. And it has a value of 35. And how do I do that? I wrote a little code myself that takes a binary list, which in this case will be bx1, and using fold function, it computes its binary value. So this is my function. So now I can use the function called decode binary. I defined a new function here. It's a column equal. Okay. So I'm going to use this decode binary on bx1, and I get 31. If instead of bx1, if I put there some arbitrary binary number, then this would be the decoded value of this binary string. It is 783. But that's not what we need right now. We're working in the range, some representative number like 35. So this is one design variable. Let's assume that I have two additional design variables. That's a total of 3 design variables. And the next one is 7, and the other one is 10. So if I put these and look at their binary representation, bx2 is 1, 1, 1, and bx3 is 1, 0, 1, 0. So my bx1 had a length of 6, whereas this has a length of 3, this has a length of 4. I don't want to build a design string that has different lengths in each segment. that violates one of the basic assumptions that we're using in the operators and so on and so forth. And one can write a program like that, but it's going to be very inefficient in terms of keeping track of, or difficult to write in terms of keeping track of which variable is which segment. So what I like doing is I bring every binary string to the same length. And what is the largest number that I can have with the 6-digit ones? That's 63. So I can make everything go from 0 to 63 by prepending some zeros in front of the bx2 and bx3. So my bx2 and bx3 are redefined. They also have length 6. But if you look at their values, they are still the same values. They didn't change. bx2 and bx3. Let me type there 3 if I can. And they are 7 and 10. So these zeros that I put in front, it's like empty plies on the outside of the laminate. It doesn't change what the design is, design variable value is, 7 and 10. Then I make an individual design for this 3 design variable case. I join bx1, bx2, and bx3. They're now all 3 have the same length, and I call this design 1. Now this design of bunch of zeros and ones have all 3 design variables in there. The first 6 digits are the first design variable. Second 6 digits are the second design variable, and third 6 digits are the third design variable. In order to be able to extract a particular design variable, I can take a portion of it. Say I want the second design variable. I know for a fact that it's from 7 to 12. So if I take that, that's this one. And if I say decode binary, percent, which is this line, it will give me the value of 7. Okay. But I make it a little bit more interesting by writing another function. It's again called decode binary, but it takes 2 arguments. First one is the binary list, which is in the entire design. And second one is the size of the design variable list, which in my case was 6. And if I do that, this module, I wrote another module in here. Red is homemade module here that I'm going to show. If I take the design variable design 1, and put it into decode binary with the variable of the individual, this length of the individual design strings being 6, I get the design variables back 35, 7, and 10. So I decoded my design. So in composite design, we're going to write something similar to this, that will take any string, and it's going to decode it into a laminate. But we're going to do that later on. So let's finish this first. So the number of design variables, let's say I have 2. Brand new problem. And I have only 2 design variables. Design variable 1, design variable 2. And I'm going to represent those by 4-digit numbers. So I'm going to create this 4-digit numbers randomly by using random. And random without any argument gives 0 or 1. So I'm going to make design 2 to be table random integer 0, 1 ndv times dv size. ndv 2 design variables. Size of the individual design is 2. basically I created a design that I call design 2, which the first design variable is 1101, and the second design variable is 1011. And now I can decode this by using this again, and I get 13 and 12. Incidentally, I think the largest number that I can get with 4 digits is, I believe, 15. So if I take design 3 and make it all ones, and look at this, this is going to be 15 by 15. So this is the size of my design space, 15 by 15. And everything is inside this. And I'm going to create 10 designs. So population size, I'm going to define population size to be 10. And I'm going to call this binary pop, a label that I just put. I'm going to create a table of 10 designs, population size, by creating them completely randomly. So initial populations are typically all random. Unless, this is an important point, this is an experience that you have to get. If you know some good designs that you want to incorporate into your initial population, this is where your chance is. Your initial population may have, instead of random design points, may have some pre-selected design points as seed design points. Seeds that you know that traditionally these are either used and they give good solutions, or you had previous design runs that you saved some good designs that you want to put into your initial population because you value them. This is where your chance, where you're going to be able to do that, putting into the initial population. Otherwise, the initial population is going to be random. Now I'm going to decode this binary, and I'm going to take the second design of that. Okay? That's 14 and 0. First design of the random population was 5 and 11. The 10th design of the population was 5 and 13. So each one of these has a different x1 and x2 value. If I want all of them together, then I map the code binary over the binary population, meaning that I take every element of the binary population that's in here, decode them, and write them in a list. So I'm going to get a list of 10 design variable pairs. This is the first design, 5 and 11. And this is the second. This is the third. This is the fourth. And I can actually make a plot of these if I want. Okay? So these are basically my initial points. And later on, we're going to actually make a plot of these, and you're going to see the evolution of the designs. Now, if this was a composite material selection, like the way that we did, I can use an alphabet different than component or material selection. Just this is not the composite yet. I think I'm doing the composite one after this J for lemon design. But if this had other discrete variables, say it's a system of components, and the component 1, you may have 5 different components. So you create an alphabet based on that. So based on this, your alphabet for system component 1 is random alphabet and that. So randomly component 1 is either 3 or 5 or 5 or 1 or so its selection is done based on this. Let's say you have, besides the component, you have a wire type that you call wire 1, wire 2, wire 3, 4, 5, 6, and they may have different values. So you create another alphabet for this, and you can component 2 is wire 6 or wire 2, different. You may have different material selection, material 1 through material 3. You can make an alphabet for it, and you can randomly get that. Or you can now create a population of designs of 10, and your first design is component 1, wire type 4, material type 1. Your second design, your component type is 2, your wire type is 2, material type is 2. Your third design is component 5, and third wire type, and first material type. So you can build your own alphabet and your own strings to be able to do these operations and write the appropriate operators to work on them. Of course, we're not going to work with wire type and so on and so forth, but we're going to go to take the easier route, and we're going to use this mostly for laminate design. So I'm going to actually create a laminate. And I'm going to call this laminate alphabet, and it will have 1, 2, and 3. And we're going to use 1, 2, and 3 to represent stacks of 2 plies of zeros, or a stack of plus minus 45, or a stack of 9-degree layers. So I'm doing away with this. And I'm defining a laminate alphabet here. And so individual laminate, if I say take a 5 stacks above the midplane, this will be 3, 2, 1, 1, 2. Okay, so it's going to be randomly, or something that I defined for a simple laminate. I will do 3, 2, 1, 1, 2. That could have been random. And if I'm correct, this should work and give me a full stacking sequence. I have a module now called decode GA. It's small d, and decode GA, given a given genetic string, turns it to angles for stacking sequence of balanced symmetric laminates. Okay? So I have a pre-specified function called decode GA. And this is the GA program. I'll take a few, let me do this. Let's see. Whatever it is called, the program GA or genetic algorithms, some program name here. So this now can decode a given laminate. I can define a population of 4 designs. So this is a population of 4 laminates. And again, randomly, they may be like that. And if I map the decode GA over this population, it will give me the stacking sequence of the entire laminate, coming from 0 to midplane, and I believe this is the midplane, and then midplane to the other surface. The reason for this is, now if I call my lamination programs, I'll be able to do the analysis of this laminate right away with my other CLT program. I can construct A matrices for this. I can construct B matrices, D matrices, whatever you want. I can actually construct the entire laminate into this. So let's see what the initial pop does. Initial pop is going to create an initial population of size P size and string length C size. So initial pop, init pop is going to construct this, but this is the, let's see which one this does. I think I may need to modify my program right here. Init pop is going to, let me try that for population size of 10 and string size for individual variable to be 5. It created a laminate. It's not the binary, but it's the init pop is for the genetic algorithms. It created 10 different laminates with 10 different designs. Now that means init pop, is there an init pop binary? There's no init pop binary that is somehow lost in the program. Let me look at it, if it exists in my program or not. I combined two programs into one, so I may have actually missed the code binary is there. Init pop, still the laminate version. I forgot to put the init pop binary is there. Okay, what I did for that though is P size, C size, and number of design variables. So for my initial population, I need to actually, So I need to do a little bit more work for init pop binary, but you're not going to be using binary, so let's stick to the, this is not working yet, but you're not going to be using binary numbers for this. So it's laminate, and if I decode use decode GA, which now has built-in decoding algorithm, by mapping over this, it can take this random initial population of 10 designs and puts out the laminate design for 10 different laminates. Remember, we are designing one laminate, but my population of designs, initial population initial, has actually 10 different laminate designs. Okay? So depending on how you develop your algorithm, you're going to be able to use this. If there are any changes in the usage, I will actually send you a separate email and program update to put the better unified version. These two are two different programs, binary and GA. So I'm trying to merge them in single, so that both will be working. All right. Questions before I jump to fitness evaluation? So this way, you should be able to generate any number of laminates for an initial population of designs with any number of laminate designs. So if you want 20 designs in your population, then you can do 20 here. And if you want the laminate size, instead of being, this has 20 layers from here to here, because each number is a stack of 2, and then the symmetric. So 2 times 5, 10, 2 times 10, 20. So this is basically 10 different ply orientations. If I want, say, 6 here, that's 24 plies, and population size of 20, then my laminates are 20 different laminates for the initial population, and each has 24 layers, mid-plane symmetric layers that I can send into my ABD matrices. All right, fitness evaluation. So let's go back to the binary, because it's easier to describe this binary, and there's not much change in this. And to do that, I'm going to actually do it for a continuous design variable, some objective function of my fitness, which is this function. And this has a specific form. That's why I use this function. And let's say I have 2 design variables for this problem, x1 and x2, x1 and x2. It's a 2-dimensional design problem. So design variable 1, design variable 2, and my objective function is in this form. I can draw the contour lines of the objective function in the range defined up to 15. That's 15 was basically 6 layers. This is my design space. You can see that I now have a fairly complicated design space. There seems to be 1, 2, 3, 4 maxima or minima here, and 1 minima or maxima here, because this is how I'm changing from one to the other one. So, depending on my initial population and the algorithm used, I may try to converge one of these points in the design space. So 2 design variables. Design variable 1 changes from 0 to 15. Design variable 2 changes from 0 to 15. Int pop binary is not going to work because it's not there anymore, which is a big problem. So I need to bring that into this program. Oh, I think it was in the program. Oh, gee. Thank you, Murray. I am so sorry. Yeah. Sorry about that. I get carried away with this. So we're gonna continue with the fitness evaluation next time, and we'll finish this tutorial next time. All right. Thank you, gentlemen, and I will either talk to you tomorrow for the test 2, finalizing test 2 if you have not, or on Thursday to complete this tutorial on genetic algorithms. Thank you again, and my apologies for going over.